All right, this lesson here is on describing quantitative data with numbers. Remember, quantitative data is data that is numbers with units that typically could be averaged out and so forth. So how do we describe data with numbers? Well, they are numbers. So the data itself is numbers. So we want to use numbers to describe the data. So first off, let's review. When you describe data, there's four things you got to mention. That shape, outliers, center, and spread. All right, now, shape is something that you need a graph to see. You need a picture of the data, histogram, stem plot, dot plot. You need something like that to describe the shape. We've already talked about shape. We know skewed left. We know skewed right. We know symmetric. We know mound-shaped. Talked about all that stuff. Outliers. How do you know if an actual value is an outlier instead of it just being, well, that's kind of high or it looks a little low? We're going to learn today how to actually know for sure if something's an outlier or not. Center. We no longer want to be vague about the center and just kind of guess in terms of what's your opinion. We now want to be exactly positive what the center of that data is. We're going to talk about that. And also we're going to talk about spread. And there's several different ways to talk about the spread of the data instead of just saying, well, it's spread from 0 to 100. We're going to actually talk a little bit more about spread. So let's dive right into it. And the first thing we're going to talk about is the mean. The mean is the number one way to talk about center. So I'm going to write that down here. The number one way, or not to say the number one way, but the first way to talk about center is with the mean. So let's talk about the mean with this example. How long do people commute to work? Well, everybody's different. Everything varies. So we went and got a sample of 15 people and we asked them how many minutes does it take you to get to work? And here are our 15 responses. Now, notice that I first made a nice little list of them all, and then I also drew a nice little stem plot of our data. And we can clearly see the shape of our data is skewed to the right with what looks like a potential outlier at 60. But anyway, we want to find the mean. So a couple things about mean. First off, the symbol we use for mean of a set of data is an X with the line above it. That is called X bar. It's actually pronounced X bar, and that is how we say that, X bar. We don't say that's a line with a little X with a little line over it. It's pronounced X bar. So anyway, how do we find X bar? Well, it's actually very, very simple. I'm sure every one of you knows how to find a mean. The first thing is you have your sum, right? So you got to go ahead and actually add up all of your values. You sum up all of your values pretty easy. So it's the sum of your observations. So sum of observations. For example, this 30 is observation 1, 20 is observation 2, 10 is observation 3. It actually doesn't matter who you call 1, 2, and 3, but they all have their own observation all the way up to your 15th observation. So we're going to add up our observations, and we're going to divide by how many total observations we have, n. Right, so we're going to add up our first observation, we're going to add up our second observation, we're going to continue on until we add up all n of our observations, and then we're going to divide by n. So for us, that is very, very simple. So we're just going to simply add all those values together, and when you add all those values together, I'm going to do it for you. You can go ahead and pause the video and do it by yourself if you want, but you get 337, and then we're going to divide by the 15 values, and when we go ahead and do that, we get 22.47, and the units on that would be the same units that the problem is measured in, minutes. So very easy to find a mean. Very, very simple. Don't need to talk a whole lot about it. It takes every value into account. So a big value might throw the mean off and make it look higher because the mean has to adjust for you adding that huge value in. Or if you have an extremely low value, then the mean is going to be a little bit smaller because of that low value, and then the mean might be a little bit lower than it really is. So the key thing about the mean is that it is affected by extreme values. Is affected by extreme values. And maybe that should be affected. I don't know. I've never was good at knowing if you use affected or affected, but extreme values. So it easily is swayed by a really high value. So this 60 down here could potentially be swaying our mean to really be higher than it is. And that is completely okay and completely understandable. What are you going to do about it? Now, a nice kind of formula. This is more of a generic formula for mean, but a nice scientific statistical formula for mean is the sum So that's our sigma. That's the symbol, universal mathematical symbol for the sum. Get to know it. It is the sum of all of our individual values, and we'll use xi there, meaning you could have your first, your second, your third, your fourth. It's the sum of your individual values. That's a little I for. And then all divided by n, your sample size. So that's kind of our key formula for the mean. It just means sum up all your values and divide by n. Very, very, very simple to do. Very, very easy to do. I don't think I need to spend any more time talking about mean. All right, the second way to measure our data, and again, this is the same set of data. The second way to talk about the center of data, the second way, and it's not to say the second most important, just the second way, is known as the median. And I'm sure you guys have all heard of the median before. Now, the median is the exact middle of your data. The exact middle of your data. So there is half your data is below it, so 50% below, and 50% of data is above it. So it is, in fact, the middle. Now, to find the median, the first thing you got to do is put your data in order. It's got to be in order. You cannot find a median if your data is not in order. So I did put my data in order: 5, 10, 10, 10, 10, 12, 15, 20, 20, 25, 30, 30, 40, 40, 40, 60. Okay, now, all I got to do is determine where is my middle. Well, when you have an odd amount, like 15, that's good news, because that means there is an exact middle. So if I do 15 plus 1, I get 16 divided by 2. So I'm going to do my sample size plus 1 divided by 2. Now this is just to find the location. This does not find the median itself. It finds the location of the median. Okay, now, by the way, we don't really use a symbol for median like we have x bar for mean. Some books will use a capital M for median. Others just say the median. So it's kind of up to you, but we traditionally don't really have a symbol for the median, but some people just use M. So anyway, n plus 1 divided by 2 does not find the median. It finds the location of the median. So 16 divided by 2 is 8, which means the 8th piece of data is where my median is. So 1, 2, 3, 4, 5, 6, 7, 8. Here is my median right here. There are 7 values below it, and there are 7 values above it. Hence, that is the exact middle. 50% below it, 50% above it. There's my median. Now, if you have an even amount of data, like let's say I had 16, well then there is no exact middle, right? See what I'm saying? So the middle would be the average of your middle 2 values, if that makes sense. So let's just pretend for a second that I had another value out here, 61, okay? So now I have 16 pieces of data. 16 plus 1 is 17. And 17 divided by 2 is 8.5. That means that the median is located between the 8th and the 9th piece of data. So I would count 1, 2, 3, 4, 5, 6, 7, 8, 9. And here's 8.5. 8.5 would fall right here. So there's 8 values below it, 8 values above it. So it would be the average of these middle 2 values. Okay, I'll say that one more time. So you would average out 20 and 20. So you do 20 plus 20 is 40 divided by 2. Guess what? It's 20. Now, technically, it's the same as the 2 values that are right next to it, but it's really not because it's right in between 20 and 20, which just so happens to also be 20. And that's what happens when you have an even amount of data. So just be careful with that. Now, a couple of things about median. Median is not affected by extreme values. So notice, for example, I added that 61, and it really didn't change the median. This 61, I could have made this 61 a 100. I mean, a clear outlier, right? I mean, somebody takes 100 minutes to get to work, well above all my other pieces of data, but that would not have affected with the median being 20. Again, I can make this outside value 1,000. 1,000 minutes to get to work, and it would not have affected my middle value. So median is not affected by extreme values. I think I spelled values wrong there. I don't know what I wrote there. Values, whatever. You get the point. All right, so we got center, we got mean, and we got median. Now, since we're on the topic of finding the median, we also have some other values. Now, these are more of position values. They're not necessarily considered center values, but they're worth talking about. And they are called Q1 and Q3. These is your first quartile and your second quartile. So your first quartile, and if you are thinking right now, quartiles, that sounds a lot like quarters, and it is. It separates your data into quarters. aisle. So what happens is, let's ignore for a second the yellow here. Let's just pretend that I had my 15 pieces of data, right? So we're ignoring these guys on the end here. Let's keep in mind I have 15 pieces of data. Okay, so anyway, the first quartile is the middle of the bottom half of your data. So once your median has been found, we're going to look at the 7 values below it. And 7 is again odd, so 7 plus 1 is 8. 8 divided by 2 is 4, which means 1, 2, 3, 4. There's my first quartile. It's the middle of the bottom half. 3 values above it, 3 values below it. Again, here's the middle right here. Here's the median. That's the middle. It's the middle of the bottom half. Now, Q3 is the third quartile. It's the middle of the upper half. So once again, I have 7 values up here. 7 plus 1 is 8. 8 divided by 2 is the fourth. So it's the fourth piece of data. 1, 2, 3, 4. Here it is right here. Here's Q3. So again, Q1 and Q3 is just the middle of the bottom half, middle of the upper half. These quartiles, actually the median, some people call Q2, but we call it the median. It's the second quartile, your 50% mark. So once again, they split your data into quarters. So you got 25% below Q1, 25% between Q1 and Q2, 25% between Q2 and Q3, and 25% above Q3. So it splits your data into quarters. 25, 25, 25, 25 should make an awful lot of sense. All right, next up is how to find the spread. So we're going to kind of bounce around here. How to find spread. Well, there are, in terms of spread, let me write that down here, spread. There are 2 big ways to talk about spread. One way to talk about spread is the first way. Again, not the numbers say necessarily the best way, but just one of the ways, is called the IQR. It stands for Inter Quartile Range. And the interquartile range is so easy to find. The formula for the interquartile range is simply your third quartile minus your first quartile. Basically, the interquartile range is the range of your middle 50% of your data. So it's the range of middle 50% of your data. Now, why is this important? This way, if you have an outlier, like 1,000 on the very far right end, the interquartile range, the middle, or the range of the middle 50% of your data, does not get affected. So IQR is very, very, very easy. It's simply Q3 minus Q1. It talks to you about the middle of your 50% of the data. Once again, it's not affected by outliers because it's focusing on the middle of your data. Now, a second way to talk about with spread is, actually maybe I should have led with this one, but that's all right, is range. Range is simply the max minus the min. Everybody knows that. The problem with range is that you could look like your data is really, really, really spread out if you have an outlier at your max or if you have an outlier at your min. Then all of a sudden your data becomes a little bit misleading. That's why the IQR comes in to rescue. It talks about the spread of the middle 50% of your data. Now, that, hopefully, was a nice, simple, kind of quick little lesson there. And now this all leads me to talking about our next topic here, which is outliers. Now, I know I'm bouncing around a little bit, but I kind of have to just so that we can learn everything at the right pace here. But our official formula for outliers, how do we find for sure if we have an outlier? Well, let me go over the 2 formulas and we'll talk about them. Basically, we have to find what we call our fences. We have an upper fence. I'll use a UF for upper fence. And anything outside or above that upper fence is an outlier. Then we also have a lower fence. I'll call it LF. The lower fence is a lower value, and anything below it is considered an outlier. So how do you find your fences? Well, we have a formula. To find your upper fence, you take your third quartile, and you add 1.5 times the IQR. So now you see why I couldn't talk about outliers until I talked to you about IQR. So to find your upper fence, you do Q3 plus 1.5 times the IQR. Remember, multiplication comes first, so make sure you do the 1.5 times the IQR first. And your lower fence is Q1 minus 1.5 times the IQR. So hopefully that makes sense. Okay, so if you are above the upper fence, you're an outlier. If you're below the lower fence, you're an outlier. So let's go back to our data real quick. So again, I know I'm bouncing around a little bit, but I want to go and show you how this actually works. So let's go back here real quick, and let's take a look at our commuting times. Now, first off, we have a Q1 of 10. We already identified that. We have a Q3 of 30. We already identified that. Now let's find the interquartile range, the IQR. This is the range of the middle 50% of our data, and that's obviously 30 minus 10 is 20. So very, very easy. So now to find the lower fence, we're going to do 10 Q1 minus 1.5 times 20. So if you want to jump to your calculator and do 10 minus 1.5 times 20, and I get negative 20. Now, obviously, there is no values lower than negative 20. Heck, my smallest value is 5. So obviously, there's no lower outliers. What about upper outliers? So I'm going to find my upper fence. That's going to be 30 plus 1.5 times my IQR of 20. So I'm going to do 30 plus 1.5 times 20, and I get 60. Now this puts me in quite a predicament here, because that's the big question is 60 an outlier or not? It's actually literally on the fence, because I do see that this is a 60. So let's just put it this way. If I made my life easy, I would have made that a 61. If that was a 61, then obviously 61 is above the upper fence. So there's kind of two lines of thought here. First off, it's so rare that this is going to actually happen where your upper fence is one of your values, but it could happen. Obviously it did right here. So in this case, you would say it's an outlier because it was at that upper fence. So again, kind of anything on the fence or higher. Some people might say, well, it's on the fence, so it's not an outlier. But for sake, first off, it's not going to happen too often. But since it is on the fence, it is on that upper fence, it would be considered an outlier. Or anything higher would be an outlier. So 60 then would be an outlier. Now, I want to just take a look at our stem plot here to talk a little bit about this stuff here. Now, it's really important to understand that this data is skewed to the right. Since it's skewed to the right, and we do notice that we do have an outlier here, the mean might not be the best center to use, because that outlier is going to make the mean higher than it really maybe should be for our data. So this is a case with skewed data where you probably would want to actually call the center the median of 20. So just keep that in mind. If data is symmetric, then your mean and your median are probably going to be pretty darn close to the same because your data is nice and symmetric. In that case, go ahead and use the mean. But when your data is skewed left or skewed right, you probably want to go ahead and use the median because it doesn't get affected by that outlier. Same thing when it comes, do I want to use the IQR here or do I want to use the range? Well, the range is going to look really, really big because of that outlier, so it would be kind of biased. So I'd rather use the IQR with skewed data because it'll focus more on the middle 50% of my data and not be bothered by that outlier. Okay, so we talked about center, we talked about outliers, we talked a little bit about spread, but I want to talk about one more aspect of spread, and that is what we call standard deviation. Okay, now I'm actually going to come up here before we look at those numbers, and I'm going to write down this. This is the third option for spread, standard deviation. All right, now what is the standard deviation? Well, I want to talk about it a little bit. First off, it's a little bit tricky to find. The process is a little bit, just takes some time, but I'll show you. I'll go through it. But what is the definition of a standard deviation? It is the typical distance a value is from the mean. So it's a typical distance a value is from the mean. So if you have a large standard deviation, it tells you that a lot of your values, or a typical value, is far from the mean, meaning you're spread out. If you have a very, very small standard deviation, that means that a typical value, most of your values, are near the mean, meaning clustered or not so spread out. So that's why standard deviation has a lot to do with spread. Now, the symbol we use for standard deviation is an S with a little x underneath it, kind of like a subscript. So the standard deviation. Now, I'm going to write down the formula for standard deviation, and you're going to be like, what? You might be a little bit confused, but I will go over how to find it. So you have a giant square root. Then what you do is you have 1 divided by your sample size minus 1, and you multiply that by the sum of your each individual value minus the mean squared. So you're like, What? So let's talk about it. You might want to jot that formula down. We'll talk about it more in class, but it's all inside the square root, and it's kind of an ugly formula, but it's 1 divided by your sample size minus 1 times the sum of each value minus the mean squared. Okay, so if you need to pause that to write down whatever, but let's actually go ahead and practice try to find it, because it can be a little bit tricky. So here's a set of data I just made up, and I already have calculated, I already know that the mean is 5. So the first thing I got to do is I got to figure out each value's distance from the mean. So I'm going to do 1 minus 5, 3 minus 5, 4 minus 5, 4 minus 5, 4 minus 5, 5 minus 5, 7 minus 5, 8 minus 5, 9 minus 5. 1 minus 5 is negative 4, negative 2, negative 1, negative 1, negative 1, 0, 2, 3, 4. So that's the difference between my values and the mean. Then I have to square all of those values. This is where we get this part that says xi minus the mean, x bar squared. So I get 16, 4, 1, 1, 1, 0, 4, 9, 16. Now the reason why I square them is because if I don't square them and I add up all of my differences, then the positives and the negatives are going to cancel out, and I'm probably going to get something at 0. And that doesn't really help me with spread. So we want to square them to get all positives. Somebody might say, well, why don't we use absolute values to get all positive? Well, I don't really have a good answer for that. I know we square them. That's how the formula works. Then you have to sum up all of these. Remember, so now we want to sum up all of these values. And when we do that, you just simply got to add them all together. So if you go ahead and do that on your calculator, you get a sum of 52. Okay? And now what we want to do is we're going to take 52 and we're going to divide it by how many values we have. So this is 52. This is the 1 over our sample size. Our sample size was 1, 2, 3, 4, 5, 6, 7, 8, 9. My sample size was 9. So I'm going to do 9 minus 1, and that's 8. So I'm multiplying that by 1/8. I don't want to say 52 divided by 8. I know that's essentially what I'm doing, but I don't want you to think that 8 is my sample size. So it's 1 over n minus 1. So that's my sample size minus 1, and then multiply that. So basically it is 52 divided by 8. 52 divided by 8 is 6.5. Now, 6.5 is what we call variance. This is your standard deviation squared. And again, this is because it came from values that are squared. This is known as variance. We'll talk a lot more about variance now or when we get in class and so forth, but standard deviation square is known as variance. But we want to get back to values that are not from squared values, because remember, all these values right here were all squared. So what we do is we square root all of this, and when we square root that, we get, the square and the square root cancels, so we get the standard deviation, not variance anymore. This is standard deviation. And the square root of 6.5 is 2.55. So that means my standard deviation is 2.55. Okay, so that means a typical point is 2.55 units from the mean. For this data, a typical point, a very normal point, or most points are 2.55 units from the mean. So go ahead and use that formula. I know it's a little bit ugly. I know I went through too fast. If you need to rewind and watch it again, you certainly can. All right, so now let's kind of have a couple summary things real quick. Now let's kind of put a bunch of stuff together. So first off, one thing we like to have in this class, again, because this whole unit right now is on describing data with numbers, and we have what's called the 5-number summary. I forgot the word number there, so 5-number summary. The 5-number summary is your min, Q1, your median, Q3, and your max. That is what we call the 5-number summary. Now, why are these important? Because they help us make what's called a box plot. Every one of you should know what a box plot is. When you make a box plot, the first thing you got to do is you got to know these values. This was 5, 60, 20, 10, and 30. This is all from my commuting problem. So you make a line, you make a number line, and it wasn't a very good one. And we're going to start at 0 and go 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. And first off, we put a line at our median. So 5, 10, 15, 20. So put a line. That's your median. Then you put another line at the first quartile. 5, 10. Here's our first quartile. Then you put another line at the third quartile. So 5, 10, 15, 20, 25, 30. And then you make a box. So your box is around your quartiles and your median. So this is how do we make a box and whisker plot. Then we need to make our whiskers. Our whiskers go to the min and the max, comma, right, parenthesis, if there's not an outlier. So I already identified that 5 was not an outlier. So that means my bottom whisker is going to go to 5. Now, what do I do with outliers? Since 60 was an outlier, I put asterisks at outliers to notify that's an outlier. And my whisker goes to the next value that's not an outlier. So that would 40. That was 40 if you recall. So 55, 50, 45, 40. So right here was where 40 was. So this is a box and whisker plot. So you got your min and you got your max. Your whiskers go to the min and max unless they're outliers. Asterisks at outliers. Your whisker then goes to the next value that was not an outlier. And you have your median in this line right here. You got your Q1 identified right here. And you got your Q3 identified right there. That's what we call box and whisker plot. Now, what's really cool is that here's the best news you've ever heard. Your calculator could do all of this for you. So what I went and did is I went to Stat, Edit. In list 1, I put all of my times. If you want to go ahead and take a moment to do that, you're feel free. Now, the calculator could do everything we just did for you. Watch how cool this is. Hit Stat, slide over to Calculate, and run a one variable stats. This is very good. It's number 1, one variable stats. Now, the only thing you got to do is tell the calculator which list to look at. So I am going to tell the calculator, please look at list 1. So I hit second, number 1. And boom, everything you need is there. First off, we have the mean at the very top, X bar, 22.47. Coming down a little bit, we have the standard deviation. That's the SX, just like I told you, 15.23. Now remember, we calculated it for another set of data when we did it in a second, but this would be the standard deviation for our data. And these other numbers we'll talk about later. They're not that important right now, but it's X bar and S. That's obviously very important. Your sample size is there. Then there's this little down arrow because we can keep hitting down and scroll down. And there's our 5-number summary, the min, Q1, the median, Q3, the max. All of it's there for you. So I know that I just taught you how to do everything. That's awesome. But the calculator could do it all for you. So cool. So please make sure I know how to do that. And if you got to rewind to remember how to do that or write it down or recall, whatever you got to do. The only thing it doesn't do is it doesn't calculate outliers. So you got to go ahead and do that on your own. All right, last thing I want to talk about is there's two things that we have here. First off, we have median and IQR. They go together like peanut butter and jelly. Why? Because they're not affected by outliers. Not affected by outliers or skewness. Then we have best friends, mean and standard deviation. The mean and standard deviation, they have to take everybody into account. So a really, really large value, really, really small value matters. So they unfortunately do get affected. So you got to be careful. When do I use the median and the IQR for center and spread? When do I use the mean and standard deviation for center and spread? Well, if your data is skewed left or skewed right, or has major outliers, you want to go ahead and use median and IQR because those things don't affect it. So they'll get nice, solid, reliable data. If your data is nice and symmetric, mound-shaped, looks really nice, M-O-U-N-D, you want to go with the mean and the standard deviation because you don't really have any major outliers, you don't have any major skewness, you got some low values to the left, you got high values to the right, and everything is nice and symmetric. That's when you use the mean and standard deviation. So hopefully that was not too long of a video, but a really nice, easy demonstration of what kind of numbers we use when we talk about describing quantitative data numerically. So thank you for paying attention. See you in class.